Thank you for the introduction. I'm very excited to be here and would like to share our recent development of wearable FUS systems for the rat brain stimulation. Since 2007, we have been researching FUS techniques for functional neuromodulation of the brain, and all our animal models involved anesthesia. We were motivated to make the transition to an unanesthetized animal model, testing its efficacy and examining the safety profile. Our objectives are, first, to develop wearable FUS headgear for the rat brain stimulation. Second, to use the system for stimulating the sensory motor cortical areas in anesthetized rats as well as in freely moving rats. Last, to test the safety through animal behavior and histology after the sonication. This is our study protocol. Male SD rats were used. A head pedestal was implanted to mount the wearable setup, and repeated FUS sessions were conducted with video recording. 3 different conditions were given. First, light anesthesia using ketamine gelazine. Second, isoflurane anesthesia. And third, awake condition, whereby the animal is allowed to move freely. Post-sonication, behavior was examined up to 2 months. We developed our own miniature transducer, size of a digit of a finger, weighing only 6 grams. Focus was formed 10 millimeter away from the transducer, and the size of the focus was 3.5 millimeter in length, 1 millimeter in diameter, at full width and 90% maximum. For the navigation, the orientation of the transducer was adjusted using a ball and socket joint, whereby the dimension of the applicator was customized to the individual head anatomy using 3D printing. For the FUS headgear, a pedestal implanted on the skull to serve as an attachable structure for the transducer. We ended up implanting the pedestal on the anterior portion of the head to sonicate the motor cortical area. A hydrogel was used for acoustic coupling. We used the stimulatory FUS parameters based on our previous studies. 600 kHz ultrasound operating with 1 millisecond tone burst duration and 50% duty cycle was given for 300 milliseconds every 5 to 10 seconds. These are our experimental settings using the FUS headgear. A sweeper connector was used to provide the power to actuate the FUS transducer for freely moving rats. Using the setup, we were able to elicit responses from the whisker, limb, and tail on the light anesthesia. About 10 to 12 watts per square centimeter ISPPA was needed to elicit the movements. No response was detected when FUS was given to off-target locations. In awake animals, we observed various motor responses, including the tail, limb, and whiskers. Other types of elicited responses were detected from the head and neck areas, including chewing behavior. A slightly lower intensity of 3.4 watts per square centimeter was needed to elicit the responses. When FUS was given off-target, no response was detected. These before and after images of the tail show the degree of tail movement in awake condition was smaller compared to the use of anesthetics. In terms of response rate, the awake sessions showed increased mean response rate while its variability decreased compared to anesthetic sessions. In terms of response latencies, the awake sessions showed shorter response latencies compared to the anesthetic sessions. We'd like to note that the portion of the responses having short latencies was increased in awake sessions. We tested up to about 15 watts per square centimeter, and all rats showed normal behavior after the sonication without the signs of BBB disruption and histological abnormalities. The wearable FUS headgear was capable of stimulating the brain and elicited responses from the rats. In comparison to anesthetic conditions, awake sessions showed, first, smaller range of movement, second, lower threshold intensity, third, higher response rates with decreased variability, and fourth, increased portion of responses having short latency. Animal behavior and histology results suggested the safety of repeated long-term use of FUS brain stimulation. We'd like to acknowledge our funding sources and collaborators. This study was funded by the generous grant from the FUS Foundation. Thank you very much.
I would like to invite question from audience.
Yeah, really interesting. What do you think you're hitting that you're causing this chewing behavior?
We think we stimulated around the motor cortical area, but there's a slight misalignment possibility, and we stimulated our chewing-related motor area. And as a control, when we stimulated kind of over ear, there's no response from the rats. The chewing response only happens when we stimulate the motor cortical area or around.
Did you calculate any kind of curves already, like looking at different durations and things like that? Is it just a difference in the threshold intensity, or do you see any other kind of changes in the response function?
We didn't actually plot the curves, but we used the kind of various range of acoustic intensity for each animal, and we just accumulate all the data, and we just reported a mean value of the acoustic intensity used for various animals.
One quick question, maybe. Did you try with a loudspeaker just to add some sound and see how the animal would react? So no direct insonation with ultrasound in the brain, but just a loudspeaker, just to see how the animal would react.
Could you repeat that?
So I can answer for that. So yeah, we did a loud auditory stimulation, including clapping, yelling.
Right.
We didn't really give calibrated sonic sound wave to the rats, but it does respond. It did respond in first few stimulation for like 1 or twice, but then the rats doesn't really respond to that anymore after few loud sounds. So
yeah, most of the cases, this rat doesn't care about the sonication when it's off-target locations.
Thank you. Thank you. Very interesting.
Thank you.
So, thank you very much.